Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss some properties of determinant, and I will also discuss some applications of determinant. So, in linear algebra, the determinant is a scalar value which can be computed from the elements of a square matrix, and in it encodes certain properties of the linear transformation described by the matrix. So the determinant is only defined for a square matrix. This is one thing. And if the determinant of a matrix A is 0, then A matrix is called singular matrix. And if the determinant of the matrix A is non-zero, then A matrix is invertible because the inverse of any matrix A involves 1 divided by determinant of A. So in order for a matrix to be invertible, the determinant should be non-zero. Four main uses of determinants are the determinant of A minus lambda I. So this determinant is used to evaluate the eigenvalues of the matrix A. And here lambda is subtracted from the diagonal entries of A, and then determinant is taken to get the polynomial. So I is the identity matrix, and if we subtract lambda is a scalar value. If we subtract lambda times I matrix from A matrix and take the determinant, then we will get a polynomial, and that polynomial must be equated to 0, and the roots of that polynomial will give us the eigenvalues of the matrix. Second application of the determinant is the scalar triple product. So whenever we are evaluating scalar triple product, which is A dot B cross C, there are three vectors. B and C will be evaluated by the cross product, and the result will be evaluated as a dot product with the matrix A. So this scalar triple product can be found out by taking the determinant of this matrix, and this matrix contains the components of A matrix, components of B matrix in the second row, and components of C matrix in the third row. And this will give us the scalar triple product. Scalar triple product is used to evaluate the volume of the parallelepiped, and if a scalar triple product is equal to 0, then the three vectors are coplanar. So scalar triple product has further two uses. It gives us the volume of the parallelepiped, and it tells us if the three vectors are coplanar or not. Another use of property of the determinant is that if A is a triangular matrix, then the determinant of A will be the product of pivots or the diagonal entries. So if we have a triangular matrix, either it is an upper triangular matrix or a lower triangular matrix. In both cases, the determinant of this matrix will be equal to the product of the diagonal entries. And we can do the derivation of this property, and this derivation is done actually at this page. So suppose we have a 5 by 5 upper triangular matrix, and these are the diagonal entries, and these entries below the principal diagonal are equal to 0. So the determinant of this 5 by 5 matrix can be written as A11 times determinant of this submatrix minus A12 times a, so this second column and first row will be skipped, and the remaining entries will be used to form another matrix, and the determinant of that matrix will be taken over here, right? Plus A13 times uh, these two columns and these two columns, the determinant of these entries. So this is the standard method of evaluating the determinants, and I think that should be easy for you. So this is our original matrix, and the determinant of this matrix can be written as A11 times the determinant of this matrix minus A12 times the determinant of this matrix. So in this matrix, we can see entire left column is equal to 0, plus A13 times the determinant of this matrix minus A14 times the determinant of this matrix. The first column will be 0, and we will have further entries as well, plus A15 times the determinant of this submatrix. So in all these submatrices, the first entire column is equal to 0, and only this first matrix has one non-zero entry in the first column. So the determinant of this matrix can be written as A11 times determinant of this matrix, and the determinant of this matrix can be written as A22 times determinant of this matrix, which I have written over here. So it is equal to A11 into A22 multiplied by determinant of this matrix, and this can be written as A11, A22, A33 times determinant of this matrix, and that is equal to A11, A22, A33, A44 into A55. So this is the product of all the diagonal entries. So that is a small derivation of this property. And if we are doing some row or column exchanges, then negative sign will be placed with the determinant. So I will discuss this property soon in this lecture. So let's discuss the fourth property. A matrix with a row of zeros has determinant equal to 0. So if a matrix which has entire row equal to 0 or entire column equal to 0, the determinant will be equal to 0. Okay, so the determinant of this 2 by 2 matrix is equal to AD minus BC, and it is represented by these straight vertical bars, and this is equal to AD minus BC. The determinant of identity matrix is always equal to 1. Either it is a 2 by 2 matrix or a 3 by 3 matrix, or in general n by n matrix, the determinant will be equal to unity. Determinant changes sign when row or column is exchanged. So if we exchange the first row with second row, okay, if we compare the matrix, this one with this, so we have exchanged the first row with the second row. So we have done one exchange. So the determinant will be equal to CD minus AB, which is equal to minus times determinant of ABCD. So if we are doing one row or column exchange, there will be negative sign in the new determinant. So the determinant depends linearly on the first row, and if we have added two entries in the first row, then that will be equal to the determinant of this original matrix plus the determinant of the new matrix with new entries in the first row. And if we have a multiplier t in the first row, then the determinant will be equal to t times the determinant of the original matrix. So this is also valid for uh, the multiplier in the first column or any column, right? Similarly, this addition property is also valid if these elements are added in the entire first column or the second column. If two rows of a matrix are equal, then the determinant of that matrix will be equal to 0. So either two rows or two columns, if they are equal, either it is a 50 by 50 or a 100 by 100 matrix. If any two rows or two columns are equal, then the determinant will be equal to 0. So here you can see the first row and the third row are equal, so the determinant will be equal to 0. And if we are subtracting a multiple of one row from another row, it will leave the same determinant. Okay, so if we have A, B, C, D as original matrix, and if we have multiplied um, a scalar quantity with the second row and subtracted the resultant term from the first row, then it will become A minus LC, B minus LD, and CD are the entries of the second row. Then the determinant of this new matrix will be equal to the determinant of the original matrix, which is A, B, C, D. So we can also visualize this, and this determinant can be written as A, B, C, D minus L, C, L, D, and C, D. So L can be taken as common, and it will be A, B, C, D minus L times C, D, C, D. So the determinant of this matrix is equal to 0, and we will have the determinant of the original matrix. So this was also one very interesting property. The determinant of AB is the product of determinant of A times determinant of B, and product rule can be stated as the determinant of A multiplied by the determinant of B is equal to the determinant of A multiplied by B. So this can be derived as well, and the derivation is extremely simple. So this is the determinant of A, this is the determinant of B, and this is the product of two matrices which is taken first, and then the determinant of the product can be represented in this way. So the determinant of this matrix is equal to this. the determinant of this matrix is equal to this, and the determinant of this matrix can be written as this. So after doing some simplification, we can simplify these two terms which are multiplied together, and we can also simplify these two terms minus these two terms. Then we will see that some terms will be cancelled out with each other, and at the end the left hand side will be equal to the right hand side. So you can do this derivation by yourself. And another property is that the transpose of a matrix A has the same determinant as A itself. So the determinant of A transpose is equal to the determinant of A. And this is the transpose rule. So now I will solve two examples. And in first example, we have to count row exchanges to find the determinant. Suppose we have this original matrix whose determinant has to be evaluated. Now we know that the determinant of the identity matrix is equal to 1. So we can do row exchanges or column exchanges to convert this matrix to identity matrix, and then we can check what can be the determinant. Okay, so let's first exchange first row with the fourth row, right? This is the fourth row which is new first row, and this is the first row which is new fourth row, and we have done one row exchange, so there will be negative sign over here. Now we can exchange second row with the third row, and new matrix will become like this, and we will have another negative sign over here. So the determinant of this identity matrix is equal to 1, and this minus minus will be equal to plus. So the determinant is equal to plus 1 of this original matrix. So let's solve another example, and we are given this matrix and its determinant has to be evaluated. Now let's exchange fourth row with the third row, right? So we will have one negative sign over here. Now exchange second row and third row. So again we will have a negative sign which becomes positive. And now exchange second row with first row, and we will have a negative sign over here, and it will become an identity matrix. So the determinant of this identity matrix is equal to 1. So the determinant of this original matrix is equal to minus 1. So that is all about our today's easy lecture on determinants of a matrix. And I hope you have enjoyed this lecture. For watching more videos, please subscribe this channel. Until the next lecture, it's goodbye.